Yeah, thanks for the invitation, and it's nice to see old friends, Lewis and Oscar. Speaking of Lewis and Oscar, this is joint work with them, Mario, and Chengjian Yao. These several results are a combination of these chaps. Okay, so this is the bottom line. So both physical and mathematical considerations, and I'll mention both of them. They lead to a system of PDE on a compact Riemann surface. And we proved that in many cases, solutions exist if and only if certain algebrogeometric conditions are met. It's the usual Kobayashi-Hitchin philosophy. We also proved uniqueness in many cases for these PDE. And this is just the tip of the iceberg, miles to go and so on. So the point is, we still need to prove results that are probably more physically realistic, but also there are connections with algebraic geometry, certain kinds of moduli spaces, as I'll mention. And there's also index theory connections, which are completely open in some sense. So yeah, so this is the main crux of what I'll talk about. Okay, so the physical motivation is the following. So the risk of oversimplifying, if you take the early universe, so it was akin to a magnet getting demagnetized. So this is the picture we learn of a magnet in high school, right? I mean, a permanent magnet has these microscopic magnets pointing all in roughly the same direction. And when you heat it beyond a certain temperature, the Curie temperature, these things, they all point in the same direction, and suddenly they start pointing in different directions, right? So you have these regions of discontinuity, right? These are called domain walls. And this region of, it's akin to the wall chamber decomposition in GIT, for instance, right? But in the physical world. So these are the so-called topological defects. Generally, whenever any phase transition occurs, these sorts of things are expected. Now, the early universe also underwent a sort of a phase transition, at least we expect it did. And so, as a consequence, you expect these sorts of topological defects to form, except they're not defects really in magnetism. It was not a permanent magnet. They're defects in the Higgs field, and they lead to defects in gravity in some sense, right? So these defects, one-dimensional versions of these defects are called cosmic strings. They're very different from the strings in string theory, no real connection whatsoever. So how do you model cosmic strings? You take general relativity, and you take electromagnetism, gauge theory. Then you couple them with a cylindrically symmetric ansatz, because it's a string after all. And then in a very special case, you get these Einstein-Bogomolny equations. Yeah. So what are the Einstein-Bogomolny equations? They demand that you find a metric on a surface, not necessarily compact, but on a surface X, a section of a line bundle, and a unitary connection. And you're given a parameter. So the equations are as follows. The equation for the metric is this one. This is the Einstein constant. So it's a singular, it's a conical metric. It's flat everywhere except at the locations of the strings where you get curvature becomes Dirac delta. So it's conically singular. The section phi is holomorphic with respect to the complex structure induced by the connection, and this is the familiar vortex equation. Yeah. So these are the equations. Now the point is, right. So notice that by the Gauss-Bonnet theorem, these ni's are not really arbitrary. So when you when you integrate on both sides and use Gauss-Bonnet, you get this, where n is the sum of these ni's. And so as a consequence, because the Euler characteristic is positive, the surface becomes S2, assuming it's compact, of course. And in this case, if you assume that these ni's are less than n over 2 for all I, or when n1 and n2 are both equal and they're both equal to n over 2, there exists a solution to these equations. That's what was proven by Young. And this should ring a bell somewhere, because these conditions are precisely the GIT stability conditions for a divisor on P1, right? So somehow, magically, that seems to be related to this physics problem. And so how did Young prove this? He reduced the system of equations to a single nonlinear PDE, a rather complicated, highly nonlinear one. It's exponential of an exponential, right? And doesn't matter what the precise nonlinear PDE, but the bottom line is, when you reduce a system of equations to one equation, you get an arbitrary integration constant, so to say, and that's this parameter lambda. Yeah? And this lambda controls the volume, the area of the metric. So what is physically reasonable is to specify what the area of the metric is, but not anything more. Here, unfortunately, what Young did was to merely find solutions for certain values of lambda, in other words, for certain areas of metrics, not for all possible admissible areas of metrics. Yeah? So he only found some solutions, not all of them, possibly. And when in this special case, this ansatz further reduces to a system of ODE, actually not a system of ODE, just a single ODE, which was solved using the so-called shooting method, again for some values of lambda. I'll mention a little bit more about this later. In the other cases, so as I said, when in this case, he solved this using another standard technique of PD, the method of sub and super solutions. And for some values of lambda, he produced a solution. And later on, others proved that there exists a solution for any value of lambda. Okay? So a significant amount of work was done on this physically relevant equation, but several natural questions remain unanswered. Can one find solutions for any admissible volume? What do we mean by any admissible volume here? If you go back to the equations here, you look at this, if you integrate on both sides here, the left-hand side is determined by the topology of the line bundle. It's one of the Chern class. It's the Chern class up to a factor. The right-hand side, the integral of that is strictly less than the integral of epsilon square over 2 times the area of the metric. So in other words, the area of the metric cannot be arbitrary. If you tell me the topology, you've already given me a bound on the area. So we expect that for all admissible areas or volumes, you have a solution, but that was not yet proven. And are the solutions unique? I mean, it's a physical equation after all. We expect solutions to be unique. That was not done either. And what about these conditions? Are they just artifacts of Young's method, or are they more fundamental? Yeah? In other words, if n1 equals n, is n1 equal to n2 necessary when there are only 2 zeros? And is this necessary? Yeah? And the next one is a related question, although it doesn't appear to be so at first glance. It might seem arbitrary. Is there a way of coupling Einstein's equations with gauge theory in the Kähler case, not in the Lorentzian case, using moment maps, such that the cosmic string equations are special cases of these things? Now, this hypothetical system is useful in study of the moduli space of triples. And I'll just soon mention that all of this is related to what Lewis was talking about a while ago. All right, so the brief answers to these questions are as follows. So the solutions are indeed unique in many cases. There are a couple of technicalities involved in the other cases. I mean, I expect that they can be resolved, but I think by the time we did all this, we were fatigued. So yeah, and if the solutions exist, they have as many symmetries as the equations themselves. In other words, you expect that if these points are at the poles, then solutions are indeed really radially symmetric, as Young expected, and N1 equals N2 is necessary thanks to two independent arguments. So the second question, if you will, it seems like a very arbitrary question, but the point is, this was done by Oscar, Mario, and Lewis before I entered the picture. I assume maybe their motivations were different, but the way I'd like to understand these things is, if you want to produce obstructions to solving PDE, the easiest way is to embed them into a moment map picture, and then you can throw the full moment map machinery at the problem. I mean, you can get a Futaki type invariant akin to the Kähler-Einstein context, and Matsushima kind of results, and so on and so forth. Okay, so, I mean, at least that's the way I would view, that would be my motivation, but I don't know what theirs was when they came up with this. Anyway, right. So you can prove that this is necessary by two independent arguments. Namely, there is a Futaki type invariant akin to the classical Futaki invariant in the constant scalar curvature Kähler case, and a Matsushima type reductivity of automorphism group result. And likewise, there cannot be a single, I mean, you can't have a single zero, same arguments. Now the point is, this part is more interesting. For any admissible volume, there exists a solution if and only if this condition is met. Okay? So thankfully, the answers to all of these questions is yes. Even the second question, and this was the one that was done by Mario in his thesis, the Kähler-Yang-Mills equations. If you take a special case, if you take a dimensional reduction of them and you set some parameters to 0, etc., you recover the Einstein-Bogomolny equations. Huh? Okay, so I'll proceed to tell you a little bit more about some more details about these sorts of things. All right, so the Kähler-Yang-Mills equations, which are generalizations of these cosmic string equations, when you dimensionally reduce them, you get the gravitating vortex equations, which is, the first one is just the usual vortex equation. The second one involves modifying the constant curvature scalar, the constant curvature equation on a surface. You should compare this to Lewis's talk. It's slightly different. The context is slightly different, but nonetheless, notice that even in his talk, the first equation was a familiar one. The second one involved modifying a familiar equation with the help of a parameter. That's because the same kind of moment map ideas underlie producing these equations. Now, an alternate perspective towards these equations is to consider G as a Kähler metric on the Riemann surface, and then substitute that here. So when C equals 0 and X is CP1, these are precisely the cosmic string equations as Mario, Lewis, and Oscar proved. And these equations do not always have solutions. I mean, there's an obvious obstruction for the first equation itself obtained by integrating on both sides. This is a very well-known obstruction. The point is, the system of equations has more obstructions than merely this. That's the point. So, okay, here are our results, which are more precisely stated. For large genus, we prove that if the first equation is unobstructed, namely if this obvious necessary condition holds, and if alpha is small, but the smallness of alpha depends purely on the parameters in question and not on the line bundle. I mean, Rui raised a point in Lewis's talk as to how small this coupling constant has to be, and here we have a quantitative bound. So in this case, you have a unique solution. And the method of proof, it's a continuity method with alpha as a parameter. In other words, you start off with alpha equals 0, you solve this equation, substitute that into this, and you solve the vortex equation. So you have a solution at alpha equals 0, and the set of alpha for which you have a solution is open. The reason is the linearization has trivial kernel, and the reason the linearization has trivial kernel is there are no automorphisms of any sort. The genus is rather high. And the challenge is then to prove that a priori estimates independent of alpha, and that requires a little bit of work. It's not trivial. And in the same paper, we also proved that this condition is necessary, solutions are symmetric, and this is not possible. We can now prove that if the genus is larger than or equal to 1, something that was not considered here, and if a laundry list of conditions is met, then there is a unique smooth solution, and this is the list of conditions. It doesn't really matter what the precise conditions are. What it suffices to note that these two theorems intersect, but there are cases where this works and this doesn't, and cases where this works and this doesn't. And the methods, this one involves a new idea of proof, which I'll describe a little later. Same thing, continuity method in alpha, but the thing is one of the estimates follows from the lower boundedness of an energy functional inspired. The similar idea appears in the study of Kähler-Einstein and CSCK metrics. Right. So we claimed in this paper that this was necessary. Unfortunately, the proof was incorrect. One of our collaborators, Chen Jian, has this nasty habit of proving us wrong. And yeah, it was really rather annoying. That's why we didn't invite him here. But so anyway, so the proof was incorrect. We can now prove it with rather sophisticated tools. Unfortunately, I can't go into too much detail, but the idea is this. So, right. So the inspiration is from the constant scalar curvature problem. So here, for example, how does one prove uniqueness, right? So suppose you have two different metrics in the same Kähler class, both having constant scalar curvature. How do you prove that? Let's say there are no automorphisms. How do you prove these two are the same? Well, I mean, this is the Donaldson-Semmes think Shushong, Chen, Mabuchi, etc. That picture. You connect these two metrics in the space of all metrics by a geodesic of sorts. It's not quite a geodesic, but let's pretend it's one. So a geodesic of sorts. Actually, what happens is you move out of the space of metrics and come back in. That's why I'm not saying it's a geodesic in this space. And then you have a functional, the Mabuchi energy functional. It's convex along this geodesic, and it has a critical point at two places. If it was genuinely strictly convex, this could not have happened, right? So that would have proven uniqueness. And the same principle shows that if you have a convex function, if it has a strictly convex function, let's say, and if you have a critical point, then it's proper. It runs off to infinity at infinity, right? So, and the slope at infinity is positive. So it's the same kind of a story here, except here we don't merely have a metric to deal with. You have a metric on the surface and a metric on the line bundle as well. So you have two things to take care of. So the so-called geodesic equation would be, you connect these two by this geodesic, by the CSCK geodesic, if you will. And for this, you solve the vortex equation with the background metric being given by the CSCK geodesic. Okay? If you do that, then a similar kind of an idea goes through. But the challenge here is, I was lying when I said this was a geodesic. This is not really a smooth curve in the space of metrics. You have to move outside the space. You have to allow non-smoothness, and you have to allow it to be not a metric. You must allow degeneracy of the Kähler form. So as a consequence, the way you prove that this sort of a geodesic exists is you take an approximate geodesic, an epsilon approximation, which lies genuinely in this space, and you tend epsilon to 0, right? So you take an epsilon approximation of this, and you have to prove estimates that as epsilon goes to 0, these things converge to something. And that's the challenge there. So there's a technical problem over there. And once you do this, then to prove that this properness kind of a result, there's a machine by Darvash and Rubinstein. And there's a general theorem which says that if you satisfy a laundry list of conditions, then your functional is proper. And it does become proper in our case, and so on. It works. So this is this philosophy. There is a moment map meaning of this method of doing things. There's a method behind the madness. This is symplectic reduction by stages. And it's actually interesting to see if this sort of a philosophy can be applied in the equations that Lewis mentioned to prove uniqueness. The challenge would be, the analog of this would be non-abelian there, so proving these sorts of estimates will be rather hairy. Anyway. Okay, so we also gave a purely PDE proof of the necessity of the vanishing of the Futaki invariant rather than appealing to general moment map picture. So Mario, Chengyan, and I proved that for every admissible volume, if this sort of a condition is met, the gravitating vortex equations have solutions. And this proof involves Shiga-Gromov theory of convergence. I mean, again, we use a method of continuity. We need to prove a priori estimates. And so what we do is, if you have a sequence of times, alpha n going to some limiting time, and then you prove enough about the geometry of the metric so that you have Shiga-Gromov convergence, and then on the limit, we arrive at a contradiction if you don't have a solution. That kind of thing. All right, so this is about the gravitating vortices and cosmic strings and our results about this. Now we'll go to this non-abelian setting. So, right, so, okay. So the thing is, if I, sorry. Right, so so going back to the motivation of this story, right? So the universe underwent a phase transition where a couple of these forces, I mean, the phase transition corresponds to the electroweak force splitting up into the electromagnetic force and the weak interaction, right? And you're expected to see these sorts of topological defects, which is what these cosmic strings are. But the thing is, in reality, these cosmic strings, what we assumed was, we go back to the very genesis of this question, right? So here, we are coupling general relativity with electromagnetism, but the reality is you should be coupling general relativity not just with electromagnetism, but you must include the weak interaction as well. So when you do that, then things become rather complicated. So a more realistic, so the word abelian in the context of what I said just now indicates that we take a line bundle with a metric. It's a U1 principal bundle. A non-abelian group would give you a higher rank vector bundle. And in the early universe, the electromagnetic and the weak nuclear forces were unified into an electro-weak force. And that split up, that was the phase transition. The cosmic strings arising from the symmetry breaking of this particular force would involve vector bundles, not merely line bundles. So in other words, this is the equation for a metric on a line bundle, and that's a problem. That's not completely realistic. So it's hoped, and Lewis says it's known at least in one direction, but so there are these non-abelian gravitating vortex equations, whatever they are. They will aid in studying these more general cosmic strings. Right, so I don't know if this is true or not, but yeah, I mean, that's the hope at least. All right, so what is the non-abelian version of the vortex equation? So if you take a holomorphic vector bundle E and you take a section of it, this is the non-abelian vortex equation. And unlike the abelian vortex equation, which is connected to superconductivity, this is the Landau-Ginzburg model of superconductivity, the non-abelian vortex equation's connection with physics is somewhat tenuous. There's I remember some vague paper of Witten, which aims to give a physical meaning to it, but it's not clear, at least not. By itself, it's not clear if it has any physical meaning, at least not that I could find. Now, Bradlow proved that exists a Kobayashi-Hitchin correspondence, that is, a stability condition holds if and only if existence holds for this non-abelian vortex equation. Yeah. Now, using the same machinery as in Mario's thesis, which was also used by Lewis, Oscar, etc., to produce their equations, the harmonic, their Hitchin type equations. Using that same machinery, you can couple this to gravity. And so you have one equation that looks like this, and another equation which involves some sort of scalar curvature kind of a term, a curvature term from the manifold plus alpha times something else, right? So these are the so-called non-abelian gravitating vortex equations that were obtained as a dimensional reduction of a more general set of equations, the Kähler-Yang-Mills-Higgs equations that Lewis, Oscar, and Mario came up with. And so hitherto, I mean, they came up with the equations, but as far as I could see, there were no existence results, at least no non-perturbative existence results. And it's a challenging problem because of the non-abelian nature of this situation, right? I mean, it's an equation for a vector bundle, so that's already a complicated affair. So I produced examples of solutions to this set of equations in a very special case. So if you take a rank 2 bundle on CP1, which is the direct sum of two bundles, ON and, I mean, it's not on CP1, it's, so I'll just tell you. So with this particular Higgs field, if you wish, Z raised to L and Z raised to N minus L, with L being less than or equal to N minus L, then, and assume a certain condition, which is this. If you take this situation, then Bradlow's stability condition would boil down precisely to a volume admissibility condition. So this is very similar to the abelian case. The volume cannot be too small, but in this situation, it cannot be too large. Okay, so it's qualitatively slightly different. So there are bounds on both ends. Yeah. So in this paper of theirs, they actually looked at this example, so to say. They considered, in fact, a more general case where instead of L and N minus L, you have L1 and L2, and the stability condition is also more general. So I took this only because it's much simpler. I mean, the point was to provide a proof of concept, not the most general result possible. So, and an obstruction, a vanishing of a Futaki type invariant led to this condition, which is why I have an L and N minus L. Okay, so that's where this comes from. It satisfies this condition. Right, so if you take this rather symmetric situation, so if you take this rather symmetric situation, then you can find very symmetric solutions. Namely, you can find there is enough symmetry so that the equations reduce to a system of ODE. Yeah, and by U1 symmetric, I mean the following action: U1 acts on P1 in the usual toric manner, and it acts to O minus n. In an obvious manner. You have a weight of this action of sorts, but otherwise it's very natural. Then using this U1 action, we reduce this system to a system of ODE akin to Young for the abelian case. So Young, I mentioned that in the case when N1 equals N2 equals N divided by 2, Young reduced his complicated equation nonlinear PDE to an ODE. It's the analog of this in the non-abelian context. We can also reduce it to a system of ODE. But the analogy ends there. Okay, so the question is this. So in Young's case, he got some ODE, whatever the ODE is, something like y double dash equals something complicated, something highly nonlinear. But the thing is, it was not an initial value problem, it was a boundary value problem, and it was on R, and as you go to minus infinity, y must behave in a certain way, and as you go to plus infinity, y must behave in a certain other way. That was the kind of a problem Young handled. So how do you solve a boundary value problem in ODE, right? The standard method is this shooting method. So suppose if you're on a compact interval and you tell me this and this, and you give me a second order differential equation, what you do is you take some value of y dash and you follow the solution, you'll end up with some value of y of b. You keep changing these y dashes and you keep getting different solutions. So you keep shooting out solutions. And the hope is the solutions depend continuously on y dash, and by the intermediate value theorem, hopefully this range will cover what we want. Okay, so this is the so-called shooting method. You take the initial value problem, you keep varying y dash, and hopefully for some value of y dash, magically you'll hit the correct boundary condition. And the intermediate value theorem plays a role. The trouble is this shooting method does not apply for systems of differential equations. Okay, so for a system of differential equations, what we would want is the same kind of a thing, except we'll have to keep changing this vector. And now you don't have the luxury of the intermediate value theorem, right? I mean, for the intermediate value theorem, you just have to look at two limits. As when you go to one extreme, this thing must be less than what we want. And when you go to another extreme, it must be larger than what we want, right? Here, it's a bit more complicated than that, right? So the shooting method is not applicable. And this would be a general problem if you take any system of ODE arising from these sorts of geometric constructions, right? So we overcame that obstacle using the continuity method, inspired from the complex Monge-Ampère equation. So you take this Aubin-Yao style continuity method, which has not been used for ODE, at least not to my knowledge. So it's a new way of looking at systems of ODE in general. So more generally, ODE or not, you take this method when S equals, so it depends on a parameter S. When S equals 0, you have a solution. You simply substitute omega as the Fubini-Study metric, and h to be your favorite metric. And when s equals 1, that's the equation that we want to solve. Okay. So when s equals 0, the metric that you choose here is the solution of the vortex non-abelian vortex equation that is obtained from Bradlow's method. And this turns out to be U1 symmetric. Okay. So as a consequence, we can now reduce this to a system of ODE, and we can try to solve that. Okay. So if you introduce a new variable, okay, so let me, these are technicalities here, but if you introduce new variables, you get one single equation. So what Yang did was, by the introduction of a new variable, he took a system of 2 equations and converted it into one equation. Here, we still do the same thing, but the challenge here is it's a system of equations nonetheless, because this is a curvature matrix. It's not merely, it's not just a 2 form in the case, as in the case of line bundles. So then you take a trivialization. We are on CP1 after all. So CP1 is a union of 2 Cs. So in the usual trivialization, you get a rather complicated equation, right? And we proved a lemma which says that if you have a solution of this, and this solution behaves in a certain manner at 0 and infinity, then it extends to a solution on CP1. So this is an extension lemma. So if you have a solution on C star satisfying this equation, and if a bunch of estimates hold, then the solution extends to CP1. And conversely, if these things hold, then you, so it's an if and only if result, right? So that's the sort of a thing. So this extension lemma now reduces our problem to solving a single PDE without worrying about anything global on C star. In fact, a single system of ODE on C star, in fact, not C star, but on R, with certain behavior at infinity and minus infinity. Okay. How do you reduce this to something on R? Again, you change your coordinates, and then you get an system of ODE with a certain complicated boundary condition at infinity and minus infinity. So cleanly, this is the final system of ODE that one needs to solve, and these are the boundary conditions. So notice it's a rather complicated affair, because you have these boundary conditions here, and then you have something about the L2 norms being bounded and so on, right? So how do you ensure all this? So how does one solve the system of ODE? Well, this depends on a parameter S, and when S is 0, we have a solution. You prove that the set of such S where you have solutions is open by using the standard method of implicit function theorem. For closedness, the estimates are rather delicate, and you first prove this estimate, and then prove all the others. So all right, so the estimates are delicate, but in any case, for every value of lambda, there is a unique solution of this ODE. And then you prove that the area of the metric you get varies smoothly. And lastly, you prove using the intermediate value theorem that all possible areas are attained. Okay. So there are 2 steps. You fix a value of lambda, you get a system of ODE, and then you solve that by a method of continuity. And then you keep varying the lambda, the area varies, and you prove it varies continuously, and it attains all possible areas that it can attain. So this is an example of a solution, and that it's only for this very specific situation, the exact analog of Yang. So for example, an open problem is, can you carry this out for the general non-abelian gravitating vortex equations, but with this ansatz? This is not known. And more generally, whatever we did in this more general context of the non-abelian gravitating vortex equations, this is a very challenging problem, and I don't know how to handle it. The other thing I mentioned right at the very beginning was this. So right here, I mentioned something about index theory. So just a few words about that. So suppose you have constant scalar curvature Kähler metrics, or even Kähler-Einstein metrics, for example. Now, if you have a CSCK metric, you can attempt to approximate it, even for that matter, even the Calabi conjecture, Ricci equals given. For all of these, you have these quantization results in the sense that you can approximate the solutions of these complicated PDE by doing something clever. That is, you take your favorite metric, omega naught, and you Codera embed your manifold into some CPN. But this embedding is not unique because you have a GLN acting on it. Yeah. So a GIT problem would fix the right GLN element acting on it to give you a so-called balanced embedding. This is a GIT question. And you pull back the Fubini-Study metrics by means of these balanced embeddings, maybe normalize them appropriately, and they are expected to converge as k goes to infinity to solutions of this, one of these, depending on what the notion of balanced embedding is. Okay, so this is the picture of quantization. Unfortunately, this picture has not been carried out for these Kähler-Yang-Mills equations or Kähler-Yang-Mills Higgs or any of these equations. If these equations genuinely describe a physical object, by the way, cosmic strings have not been detected yet. There have been many false alarms in the astronomy community. They have not been detected yet, but if we expect that these are genuinely describing physical systems, we need to come up with an algorithm to compute them, otherwise it's completely useless, right? So, but unfortunately, there is no quantization result here. I think Mario has tried his hands at it, but did not succeed. Something fundamentally new here, quantization-wise, and it's not clear what to do. So this part is completely open. But yeah. All right, yeah, I think I'll stop here.
I would like to make a comment. You were wondering about the physical meaning of the non-abelian vortex equations. Right. So if you believe that instantons on 4 manifolds have anything to do with physics, then there you can find a meaning, because the solutions to the non-abelian vortex equations are instantons on the product of the Riemann surface by the sphere, invariant under rotation. So there's a dimensional reduction of the instanton equations. That's actually the principle under which we actually found these gravitating vortex equations as well. Right? Yeah, that's let me this.
You said that quantization for Kähler-Yang-Mills is completely open, but you expect that at least the method of reduction by stages works, or
that's the hope, but it's not clear to me. It's not. I've thought about it, but yeah, I don't know.
Okay.
What the right GIT problem to set up the situation? Yeah, it's not clear.
But it's not that you found something wrong.
No, I didn't find anything wrong.
Okay.
I didn't find anything right. Maybe let me put it this way.
But okay.
Yeah.
I think it should work.
Yeah.
So I had a question about the physical motivation and its connection to what came later. You said this was about the early universe. But where's the Riemann surface in that picture? I mean, the early universe has some FLRW
I
metric.
should have meant, so it's
It's a toy model.
It's a one-dimensional object, right? And so in other words, it's, if you were to write the solutions of the Einstein equations, they would be, you would write a cylindrical ansatz of this type. Space-time is expected to be this. This is time. This is the, if you wish, the string direction Z. This is a surface. It's like the cross-section of the cosmic string in some sense.
Is the topology of the early universe really like that? I mean, I thought it was
this is
something.
only to model us a few isolated strings. I'm not including the rest of the universe here. So this is a sort of a local kind of a thing. If you are in a neighborhood of a cosmic string, this is how it will look.
But this theory is for compact Riemann surfaces. Yeah?
Right. So I'm assuming that this is a large sphere of a very large radius to approximate a plane, which is a more reasonable thing than to take the entire plane itself and assume some decay at infinity, because at infinity you might have galaxies or something else.